Hello and welcome back to Dr. Logic awkwardly does logic with all of her tech balanced precariously on her knees, so let's hope nothing falls. In this video, we're going to do the last of the soundness proofs of basic rules for propositional logic, namely the soundness of negation elimination. Now, the cool thing about this proof is that the proof of the soundness of negation introduction is almost entirely identical. You just have to play around with where you put some of the negations. So if you're looking at using these example proofs as kind of guides for constructing soundness proofs of the rules that we're not doing in the videos, this is a very easy one to start with. If you understand negation elimination, doing negation introduction should be straightforward. So let me bring up the whiteboard, ignore what is on there because there's a bunch of leftover stuff. There we go. Let's start fresh. Soundness of negation elimination. So we start off by explaining what a proof that uses this rule would look like. So we say that let n be a line of a proof annotated by negation elimination lines I to j, because remember, negation elimination cites a subproof. So what this means, another way of saying this, is that there is a well-formed formula phi on line n where not phi, because remember, we're going to be eliminating that negation, not phi occurs on line I as an assumption. And I just realized that there was a couple other things I should have noted about the shape of this proof. So let's just put an asterisk here and come down here and say where I is less than n, j is less than n, and I is strictly less than j. So sorry to have forgotten that. Anyway, phi occurs on line n, not phi occurs on line I as an assumption. And we also have that there is some well-formed formula psi where psi occurs on line k. Let's skip down here, where k is in that subproof, and the negation not psi occurs on line L, which is again also somewhere within that subproof, but it's not the same line because you can't have two different formulas written down on the same line. So this is what the structure of the proof looks like. At some point after our assumption of not phi, we end up with a contradiction between psi and not psi. And this could be a contradiction with the initial assumption. It could be that the last line of your proof is where one of the contradictory formulas occurs. We're leaving all of that open. But now we are going to assume that everything in the subproof, because the subproof is less complex from the proof in which we want to apply negation elimination, everything in that subproof is sound. So what this means, here, actually, let's spell this out a bit more. Because the subproof from I to j is less complex than the proof all the way up to line n, we assume that it is sound. Because if it isn't, well, then we should be looking at the subproof to figure out what the problem was in there. And so, we would eventually get back to some starting point where we can be sure that everything that we've done, that we've applied so far, is legit. So we're just going to assume that we've already shown that for the subproof. But what it means to assume that this subproof is sound, that's the same thing as saying that every truth value assignment that makes the assumption true also makes every other sentence in the subproof true. So every other well-formed formula in the subproof true as well. But now you can already see where the problem is going to be. So if psi is true and not psi is true, well, then their conjunction, psi not psi, is true. And you can see this just by inspection of the truth tables. If inspection of truth tables. If you have two true conjuncts, you put them together into a conjunction, you get a true conjunction. We saw this when we proved the soundness of conjunction introduction. But any conjunction of a formula and its negation, such as psi and not psi, will never be true. This is a contradiction and will never be true. So since the truth of the assumption would mean that, on the assumption that the subproof is sound, that the contradiction would have to be true as well, we know, so we now know that there is no truth value assignment that makes not phi true. Because if there were one, then it would also make a contradiction true, and that you can't have in classical logic. It's one of the things that makes it classical. So what we know is that every truth value assignment will make phi false. Sorry, if there's no, sorry, we'll make not phi false, and hence phi true. But phi is the well-formed formula on line n, and what we wanted to prove is that if everything that we have done in the proof so far, including the subproof from not phi to the contradiction, is sound, then our application of negation elimination will also be sound, that is truth preserving, that is our formula phi will be true. So QED. So I encourage all of you to take a look at this proof and try to rewrite it, possibly not less messily and better organized than me, because you can go back and rewind and erase and all sorts of things that are difficult to do on a video, and try to prove the soundness of negation introduction. You'll see that it's basically exactly the same. There's only one or two little bits that you need to change, and it's a good exercise. So give it a go. And gosh, this is the last of the individual rules that I'm going to prove at this point. I may do one more video talking about other meta results that you can prove about propositional logic, but this is kind of bringing us to the end of this topic. Very soon, we will get to have a discussion about the shortcomings of propositional logic, the ways in which it doesn't do stuff that we would like to be able to do in logic. And this will provide us a nice segue into predicate logic, which will be our next topic of consideration. Anyway, next videos, one or two, will probably be me nattering on about these linking topics, but I hope to see you then anyway. Take care. Cheers.